Hello and welcome to another problem solving session with Special Maths Academy. In this video, we'll be solving one of the problems from the Nigerian Mathematics Olympiad, the third round, 2021. So let's dive straight into the problem. Okay. So it says, find all pairs of natural numbers p and n with p prime such that p to the sixth power plus p to the fifth power plus n cubed plus n is equal to n to the fifth power plus n squared. And here we have two quotes, one from Einstein. Einstein says, God does not play dice with the universe. And for someone who's doing maths, if you're quite familiar with primes, you'll see that primes are very unpredictable. And here we have Paul Edosh saying that God did not play dice with the universe, but something strange is going on with the prime numbers. And of course, I agree with Paul Edosh. Okay, so let's just go into the problem, that side. So let's express this Diophantine equation in a way that might be more convenient for us later on. So we have p to the sixth power plus p to the fifth power. So we'll just take all the n's to one side. So it's equal to n to the fifth power minus n cubed plus n squared minus n. Okay. So we have p to the sixth power. So let me just factor this out immediately. So we have p to the fifth power into p plus 1. And here we can factor out n immediately. But by the way, before I move on, it's easy here to see, since we're dealing with natural numbers, we have that n cube. So I'm just, we have that n cube is greater than or equals to n squared. So it means 0 is greater than or equals to minus n cube. So I'm just negative n cube plus n squared. And we have that since we're dealing with natural numbers, 0 is greater than negative n. So we have that p to the sixth power plus p to the fifth power is equals to n to the fifth power minus n cubed plus n squared minus n. This is less than or equals to 0, and this is less than 0, because I'm dealing with natural numbers. So we have that this here is less than or equal to, or strictly less than n to the fifth power. Okay, and here on this other side, here that we have that p to the fifth power is less than this. Okay, so we can connect these two, and we have p to the fifth power is less than n to the fifth power. So I just wanted to bound it, and let's see if that will help us. So I'll just take note of that here. So p to the fifth power is less than n to the fifth power. So we have p is less than n. So basically here we have p is less than n. Okay, so this is just by the way. This may help us later on in the problem, but yeah, we'll just take note of it and then we'll move on. Okay. So you can always pause the video before I clean to make sure I follow completely what I'm doing. Okay, so we have this. We can factor out n on the right hand side, and we'll have this n to the fourth power minus n squared plus n minus 1. Okay, so this is equal to n. So we can factor out n squared here. So n squared into n to the fourth power sorry, this should be plus n minus 1. Okay, so I'll just put this like this. So, okay, so we see that here we have difference of two squares, and n minus 1 divides n squared minus 1. So here we can factor out n minus 1. I'll be left with what? N squared into n plus 1 plus 1. Okay, so this is equal to n into n minus 1. And here we have n squared times n, so this will be n cubed plus n squared plus 1. Okay, so I'll just put that somewhere here. So let me put it here in the problem. So we have p to the 5th power into p plus 1 equals to n into n minus 1 into n cubed plus n squared plus 1. Okay, so let me just erase this, what I have here. Okay. Okay. Now, next, what I'm going to show is that n is greater than or equals to 3. So recall that n is a natural number. So we'll just test for n equals 1 and n equals 2. Okay, so when n is equals to 1, if n is equals to 1, what does this imply? It implies we have p to the 5th power into p plus 1 is equal to 1 into 0 into 1 plus 1 plus 1. So here we see that this is equal to 0, and we see that this is a contradiction. Okay, so n cannot be 1. If n is equal to 2, so if n is equal to 2, we have p to the 5th power into p plus 1 equals to 2 into 1 into 8 plus 4. So that's 2 cubed is 8, 2 squared is 4, and then plus 1. So this is going to be equals to 2 into 13. Okay, so we see that p to the 5th power, no 5th power of a prime is in the factor, is among the factors of the right hand side. So we see that this is also a contradiction. Okay, so it implies that it implies that n is greater than or equals to 3. So I'll just put 3 less than or equals to n. Okay. So we just tested for n equals 1 and n equals 2, and we saw that that did not give us solution. Okay. So next, the next thing I want to prove is that P, so P must divide a pair of the elements of the set of factors on the right hand side. So basically this. So P must divide at least a pair. So we're saying P. So basically this statement, what I mean by this statement is that P divides any two. Let me do this. So what I mean by this statement is that P must divide a pair at least. So basically P can divide all three, but P must divide at least two of the elements of this set. So to prove this, basically, we assume, for the sake of contradiction, that P divides only one. So the reason why we're going straight to saying P divides, so for sake of contradiction, we assume, so suppose P divides exactly one of the elements. Okay, so the reason why this is it's enough to assume this for the sake of contradiction is because it's obvious that P must divide one of the elements, because we have that P divides the left-hand side of this equation, and so P must divide the right-hand side. So P must divide one of the elements. So we're saying suppose P divides exactly one of the elements. Okay. So the first case, so we can say suppose P divides N and P does not divide N minus 1, and P does not divide N cubed plus N squared plus 1. Okay, so what can we do from here? This implies that the highest power of P dividing, so we'll just call it a p-adic value. Okay, so this implies that P so I wanted to use p-adic value, but I decided to have a change of mind because it's not really necessary here. So this implies that P, the statement P dividing the product on the right-hand side is equivalent to, since P does not divide this and P does not divide this, and P is prime, so it's equivalent to P divides N. Okay, but we can even make this statement stronger. Why? So let's see how we can make it stronger. So basically, P to the fifth power divides P to the fifth power into P plus 1. Okay, so this implies that P to the fifth power divides N into N minus 1 into N cubed plus N squared plus 1. Okay, but since we already assume that P does not divide N minus 1 and P does not divide N cubed plus N squared plus 1, so it implies that we can strike out this whole. So we'll have that P to the fifth power divides N. Okay, so what does this imply? This implies that P to the fifth power is less than or equals to N. So this implies that P to the fifth power over N is less than or equal to 1. Okay, so P to the fifth power over N is equal to what? So from this Diophantine equation is equal to N minus 1. So let me just write this better. Is equal to N minus 1 into n cubed plus n squared plus 1 all over p plus 1. Yeah, so just checking that that is true. So this is equal to this from the Jaffantan equation. So we're saying this is less than or equals to 1. So what does that imply? So we can cross multiply, we can take the inequality. So it implies that n minus 1 into n cubed plus n squared plus 1 is less than or equals to p plus 1. Okay. Sorry. Yeah, p plus 1. Okay. So what does it imply? So I'll just scroll down a bit. It implies that, recall that we said n is greater than or equals to 3. So 3 is less than or equals to n. So this implies we can put, so we have 2 minus 1 into n cubed plus 1 okay, so let's put it this way instead. So we can put, so this implies that, recall that from p less than n, so this implies that 2 minus 1, let me scroll down a bit again. Okay. So from p less than n and 3 less than or equals to n. So this implies 2 minus 1 into, so I'll just replace, the reason why I put 2 because 2 is less than 3, which is less than n. So we can say, can put 2 less than n. Okay, so 2 minus 1, and then we'll just put p here. So p cubed, and then I'll just throw away this n squared. So I'm just trying to bound it, okay? So this is less than or equals to n minus 1 into n cubed plus n squared plus 1. And this is less than or equals to p plus 1, okay? So here we have p cubed plus 1 less than or equals to p plus 1. So we cancel out the 1 and we get a contradiction. That's p cubed. So the cube of a prime being less than the prime itself. So this is a contradiction. Okay. So this one gives a contradiction. So I'll just clean this part of the board and then move on. So the other ones will be similar. So suppose p divides n minus 1 and p does not divide n. Okay. So this is just going to be very similar. So we have p to the power of 5 divides p to the power of 5 into p plus 1, which is equals to n into n minus 1 into n cubed plus n squared plus 1. So since we're assuming that p does not divide n and p does not divide n cubed plus n squared plus 1, it implies that we can throw away those ones. So we have p to the power of 5 divides n minus 1. And once again, we have p to the power of 5 less than or equals to n minus 1. Okay. So here again, we have p to the power of 5 over n minus 1. So recall that the first case we did p to the power of 5 less than or equals to n, and we got the contradiction. So here it's just going to be analogous, but I'll just try and rush through it. So let's breeze through it. So we have this implies 1 less than or equals to n minus 1 over p to the power of 5, which is equal to p plus 1 all over n into n cubed plus n squared plus 1. Okay, so we take this and then we attach it to the inequality. So we have n into n cubed plus n squared plus 1 being less than or equals to p plus 1. Okay, so as before, we can see that this already is a connection, because in fact we can just quickly see that n squared plus 1 is less than or equals to n into n cubed plus. So in fact, let me just put it this way. Let me make it strict. So n plus 1 is strictly less than n into n cubed plus n squared plus 1 less than or equals to p plus 1. So we have that n plus 1 is less than or equals to p plus 1, which implies n is less than or equals to p. But this is a contradiction, because we have the first thing we showed was p is less than n. So this is a contradiction again. So we move to the last part of this. So let's move to the last part. Okay, so the last part will be p divides n cubed plus n squared plus 1, but does not divide the other two. So we have, this implies that p to the 5th power divides p to the 5th power into p plus 1, which is equal to n into n minus 1 into n cubed plus n squared plus 1. Okay, so we can throw away n into n minus 1. Okay, and so we have p to the 5th power divides n cubed plus n squared plus 1. Okay, so this implies, by virtue of the divisibility, implies that p to the 5th power is less than or equal to n cubed plus n squared plus 1. Okay, and this implies what? So just try and finish it off from here. So n cubed plus n squared plus 1 all over p to the 5th power. This is equal to p plus 1 all over n into n minus 1. Okay, so what does this imply? This implies n into n minus 1 less than or equals to p plus 1. Here we have n squared minus n. It's less than or equals to p plus 1. Okay, but recall we already have p is less than n. So if we add these two inequalities, what do we have? Since they have the same direction, we can add the inequalities. So we have n squared minus n plus p. Since one of the inequalities is strict, then when we add it, the final inequality will be strict. So we have this is strictly less than p plus 1 plus n. Okay, so we have p will cancel out. So we have n squared minus 2n, okay, is less than 1. So we can add 1 to both sides. So plus 1, this will be less than 2. So we have n minus 1 all squared is less than 2. Okay, but recall we said 3 is less than or equals to n. So this implies 3 minus 1 all squared is less than or equals to n minus 1 all squared. Now what does this give us? So 3 minus 1 all squared is 2 squared, which is 4. So we have 4 is less than 2, which is a contradiction. Okay. So here we've shown that P must divide a pair of the elements of the set. So let me just erase this and then move on to the next thing to prove. Okay. So we use contradiction to show that P must divide all the elements of these two sets. Okay. So next we go to finding GCD of the pairwise. So the next thing, GCD of n and n minus 1. Okay, so the greatest common divisor of n and n minus 1 is equal to what? 1. The GCD of n and n cubed plus n squared plus 1. Okay, so we see that GCD of n, so we can factor out n from n cubed plus n squared. So this will be n into n squared plus 1 plus 1. So this is equal to 1, because we see that n divides this into, like, so n divides n into n squared plus 1. But since we're adding 1, so basically, we can just use Euclidean algorithm to show this quickly. So this is equal to the GCD of n. So this will be n squared plus 1 plus 1. So minus, so just subtract the multiple of n. So this is equal to GCD of n and 1, which is equals to 1. Okay. So GCD of this is 1. Okay, so I'll just erase this. Next, we find the GCD of n minus 1 and n cubed plus n squared plus 1. Okay. So let's do that here. So let's use a bit of Euclidean algorithm. So GCD of n minus 1 into n cubed plus n squared plus 1 is equal to GCD of n minus 1 into n cubed to n cubed plus n squared plus 1 minus, so n squared into n minus 1. So this is equal to the GCD of n minus 1 into, so here we see that n cubed will cancel out, and here we see that we'll be left with 2n squared plus 1. Okay, so this is equal to the GCD of n minus 1. So just, so minus, so 2 into n plus 1 into n minus 1. So I'm just using n minus 1 to reduce the other guy. So this is equal to the GCD of n minus 1. So when we reduce this, this is basically, so let me just do it up here. So 2n squared plus 1. So this is basically difference of two squares. So minus 2 into n squared minus 1. So this is minus 2n squared. So minus negative 2 times negative 1. So plus 2. So we just be left with 3. Okay. So because 3 is prime, the GCD is equal to, any factor of 3. So it's equal to 1 or 3. But recall that the third point we made was that P must divide a pair of the elements. So we've already gotten that the first two GCDs are always going to be 1. So the GCD of the third one cannot be 1, 2. If not, it will be contradicting the third statement. So it means the GCD of n minus 1 and n cubed plus p squared plus 1 must be equal to 3. Okay. So just erase this. Okay. So now since the GCD of this is equals to 3, I told P must divide the pair of the GCD. P cannot divide 1. So P does not divide 1. P does not divide 1 here. So P divides 3. The reason why P cannot divide 1 because P is a prime, and if P is dividing 1, to force P to be 1. So since P divides 3 and P is a prime, this gives us that P is equal to 3. So this implies we have P is equals to 3. Now, since P is 3, we can solve this equation. So we have 3. So 3 to the 5th power. So this would be 3 to the 5th power into 4. So 3 plus 1 is 4. So we have this is equals to n to n minus 1 into n cubed plus n squared plus 1. Okay. So here, basically, we just have a polynomial to solve for. Okay. So there are a lot of ways we can go, we can, work our way through it. But rather than solving it as, a regular polynomial at this point, it's better we still use, ideas of number theory, because solving as a regular polynomial, you have a quintic polynomial here, and it's not going to be nice trying to factor it out. So let's look at this. So here we have 3 to the 5th power into 4 equals to n into n minus 1 into n cubed plus n squared plus 1. So how that this is greater than or equals to. So this is greater than or equals to n into n cubed. Okay, so I'll just put it this way. So 3 to the 5th power times 4 to 4. So I have that 3 to the 5th power times 4 is greater than or equals to n to the 4th power. Okay. So here we can test, values. So suppose n is greater than or equals to 5. So let's just, try and get a contradiction here. We have 3 to the 5th power into 4 is greater than or equals to 5 to the 4th power. Okay. And here we can try and calculate. So 3 to the 5th power. Actually, there's no point of doing this. So let's just try and bound this. So that's not the numbers to try. So 3 to the 5th power is, so this is 3 to the 4th power is 81. So 81 times 3, this is 243. So 243 times 4. So this will be 4 times 3, which is 2 carry 1. 4 times 4, 16 plus 1, 7. And 4 times 2, 8, plus 1, 9. So we have 972 is greater than or equal to the fourth power. Okay. So we can easily see that the fourth powers of, okay, so for instance, the fourth power of, recall what I've already said, 3 is less than or equals to n. So n can be, so we're going to just test 3, 4, 5. Now this fourth power of 6, that is 216 times 6. So this is 1296. We see that the fourth power of 6 already surpasses 972. So we'll just test 3, 4, and 5. Okay. So when we test 3, we have 3 to the fifth power into 4 equals to 3 into 2 into, so 3 cubed. So this will be 27 plus 9 plus 1. So 27 plus 9 plus 1, that's 37. So we say this is a contradiction. Okay. So we test for when n is 4. So this will be 4 into 3 into 4 cubed, that is 64. 4 squared, that is 16 plus 1. So this is going to be 81. So we see that 3 times 81 is 3 to the fifth power. And we see that 4 is already here. So this works. So we see that one of our solutions is so P, comma N. So we have one of the solutions to be 3, 4. So we test 5 to see what happens. So see that 5 into 5 times 5 minus 1, that is going to be 4. And then we have 125 plus 25 plus 1. Here we can already see that 5 is not a prime factor of the left-hand side. So this, instead of expanding everything and calculating it, we really see that this is a contradiction. So we see that the only solution is 3, 4. And that'll be all for this video. See you in the next video. Goodbye.